Okay, 4 o'clock. Welcome back to yeah, your favorite class. Come on. uh, I thought you guys would have picked that up by now. Welcome back to your favorite class. Rawr. Couple of announcements. First, your homework number 1 was due today. I'll try to turn that back to you guys 24 hours. Is kind of like what I shoot for. So just look for an email response from me. I'll come back with your grade in that email. So I'll provide some comments and some feedback and your grade in a response email probably in the next 24 hours. Okay. I've posted your first simulation for this class on friction, so go ahead and take a look at that on Canvas. It'll be due next Thursday, so I think that's the 18th or 17th. So I'm very detailed and specific about what I'm asking you for in the simulation. Some part of it you have to do by hand, some part of it you have to do with MATLAB and some coding. I'm very specific about what I'm asking for, so make sure you take a look at that and do that fully, okay? I kind of like those simulations. It's a little bit different. You get to use MATLAB, see how it's maybe applied to real life, and I hope you guys kind of enjoy that little change of pace. It's nice. I always kind of like the nerdy computer coding, so, it's just me, but I also have a PhD in engineering, so that means I'm a nerd, so there you go. All right. Finally, I am going to post a second homework on the topic that we're going to start today. I'm probably going to post it tonight, so you'll look for that, and that'll be due like a week from today. All right. Any questions about what we got going on? How do we like the meme today? That's funny. Okay. A little holiday humor on this. I also got a new mic. If it's a little fuzzy or cuts out or whatever during the lecture today, please let me know in the chat. So I don't like talking. You can't hear me. Please let me know. Okay, so new topic. We finished friction. Friction is over. On to better and bigger and better things. And the new thing that we're going to talk about, we have to take a little bit of a deviation. So we dipped our pool a little bit into the idea of possibly moving with friction. But before we really get into the idea of motion, we have a couple of precursor things that we need to get out of the way. And that is the idea of centroids and area moments of inertia. And these are kind of like geometric factors that come up when we start talking about motion. And we have to be able to deal with these when we're moving and going through the ideas of motion. So we're going to take a little detour for a short time into some kind of heavier math with centroids, area moments of inertia, and then we'll move on to actually seeing stuff move. I promise. Well, it will happen. Don't you worry. There's like all this build up to it. Okay, so I posted a new set of lecture notes. You can follow along with that if you'd like on centroids. And we will just go ahead and get going on that now. All right. So even in the first couple of weeks when we were looking at objects that were kind of sliding up and down ramps and little blocks that were about to tip over or whatever, we were more or less assigning weights to these objects and saying that like the weight of the object was right in the center of the object. And a lot of times in engineering applications, that's true. And you can just say like, all right, if this thing is of like uniform density, we'll just say, yeah, the weight of this guy can be represented as a vector W right in the center of this refrigerator. Okay. But a lot of times that is not necessarily easy to discern where you should be sort of like making that equivalent force. So like, let's say you have a refrigerator that has a big old turkey on one half of it that you haven't cooked for, Thanksgiving yet. Well, then the center of weight of that particular refrigerator is not necessarily going to be in the middle, and it's not an accurate representation to sort of like draw a weight vector right in the middle of that fridge to do analysis, right? You kind of have to accommodate the differences there. And so it's useful for us to go through some exercises to talk about how can we basically assign where we're going to put this like equivalent weight for this object as we're doing our analysis by sort of looking at the individual components that make up that object and saying, all right, we got a big turkey here, we got a big, stuffing over here, we got Jello over here that's maybe not as heavy. How do we like accommodate all that stuff in our fridge? And not necessarily for shapes that are, cubic or rectangular, like maybe your fridge is, but what if you have a kind of a crazy looking shape, like this chair that I'm sitting in? I mean, this chair's got like a crazy shape. Like, where's the center of gravity of this chair? It's hard to like say or understand that or know that. Okay, so that's what we're going to focus on over the next, lecture or two, is talking about how do we locate the centers of mass and the centers of gravities of these particular objects. So let's put that in writing. So up to now, we've more or less assumed that you can replace the weight of an object with sort of like this equivalent force load right in the center of the object. So we have assumed weight of an object to be a single force at the object's, I'll say, what does it really mean to be at the center of an object? It's a debatable question. So an example that might come up like as an example for a truss. Trust me when I say that this is complicated. Oh gosh, gotta do something, okay? Gotta entertain myself somehow. Okay, maybe you have some truss that, so here we have our typical truss system that's like a box truss, I don't know. Something maybe that looks like this. So there's a pin in the lower left, maybe a roller in the lower right. This is like your typical truss structure that you might have seen in your statics class. And let's say you got some forces on here that are acting. Let's call this P, Q, and maybe some force R. All right, so you got some forces that are acting on this guy. All right, and this is like your space diagram. It's a pictographic representation of some system that you want to analyze. And if you want to make a free body diagram out of that, you're going to want to sort of like cut away what's happening at those edges. Get the pin and the roller. And maybe you want to separate those forces, P, Q, and R, into their X and their Y components. That might be something that you do for your analysis. So if you wanted to do a free body diagram of this, maybe you have like some PY, some PX, but not P90X, some QY, some QX, some RY, and maybe some RX. You're just separating these into their particular forces. Let's say that we've got points A and B down here just for clarity's sake. Here at the pin, we got a force at A in the Y direction. Here, force at A in the X direction, and at the roller, force at B in the Y direction. All right, these are all kind of like the external forces that might be acting on our truss. And all things being considered, we would still have to sort of account for what is the weight of this truss in our free body diagram. It's like this internal force. And, in passing, you might just say, all right, well, all these beams on this particular truss probably have the same weight or same density, and it looks symmetric, so let's just slap a W in the middle there and call it the weight. Okay? And so you might just put like some weight here in the middle, W, and say, all right, I'm ready for analysis. And that's a little bit lazy because we know that maybe one of the members is made out of steel, one of the members is made out of aluminum. So maybe one of the members is more dense and thus has more weight than another. And so the center of weight of this particular object might not necessarily be right in the center where I've sort of drawn it now. And also, like, how do I know the height of the location of this particular weight? Like, is it the appropriate height right in the center? Maybe there's some other things that are going on that could change the weight. Maybe it's deeper into the page in one location or not. Who knows? Okay. So basically the question is, how can I locate this accurately? Okay. So let's put some actual words to this. In actuality, the weight is distributed among the body. Right? Each of these individual members is going to have some weight associated with it, whatever. But for analysis, it is often convenient for us to find a center of mass and replace sort of like the distributed weight of the object, so like the kind of the weights of all the individual bits, with an equivalent weight at the object center of mass. The center of mass or gravity. Kind of goes by both things. There's subtle differences in those two things, but more or less the same. For many objects in many situations, it's like rather intuitive to sort of like do this. You say like, you know, this refrigerator weighs 50 pounds and we put that 50 pounds right at the center of the refrigerator and we go on our business. All right. Right. Example, like a homogeneous aluminum block. Okay, say I had some aluminum brick in front of me. It's pretty easy to understand that if it's like fully dense and equal density everywhere and all that sort of stuff, that the center of mass of that guy is right in the middle, and I could, for all intents and purposes in my analysis, just replace the total weight, which is like distributed equally among this aluminum bar, with an equivalent weight right in the center. But for many objects, it's more complicated. And it might not always be intuitive where that sort of center of mass is located. So we would like some mathematical method that would allow us to find that centroid regardless of density, geometry, etc. Okay? So here, in this lecture, we derive methods for calculating location of center of gravity and mass. We're going to distinguish what each one of those two things is. They're kind of separate things. Center of gravity and center of mass are usually one and the same, but not always. Okay. All right. So that's what's coming. The class is going to get a little mathy. So I hope you wore your math pants and you brought them today because it's time to get a little mathy. We're all engineers, right? We're supposed to not be afraid of math. So rawr, let's go. Math, etc. So let's do this. Let's first talk about the center of gravity of a flat plate. All right, so we're going to go through the derivation here to sort of calculate, using a lot of tools that you already know and that you already have, to determine how to find sort of the location of the center of gravity given information about the density and sort of the geometry of the piece. All right, so let's consider a flat horizontal plate. Flat horizontal plate. And that's what we'll draw now. Okay, so I'm gonna kind of make this in 3D as best I can. Again, my artistic abilities on a scale of 1 to 100, about a 42. Anyone? Hitchhiker's Guide? Okay, come on. All right. Actually, let me change the coordinate system here slightly. I want to make sure I match the notes. So let's go X here, Y backwards, and Z up. I want to make sure that I'm kind of matching the picture in the notes. And let's say that I have in the XY plane this horizontal plate. And let's just give it some arbitrary sort of random geometry in this plane. Okay. So here's my plate in this particular plane, and I'll try to give it some thickness here. Okay. So there's my plate. Let's say that this is fully contained in the XY plane. All right. Any particular point on this object, I could investigate this plate and look at any particular small area on this object and say that any point on this particular plate has some small amount of weight associated with it, which we could call like a delta W. So let's say that there's this particular point here. Let's say that this point in space is like x1 comma y1. And the weight associated here is delta W1. And I'll just draw that sort of in a vector form right in this point. So here is delta W1. It's a very small amount of weight concentrated at that particular location that represents just a small amount of weight at that particular point. All right. I might have another point back here. It's got some small amount of weight on it. Let's call this delta W2. And this particular point is like x2 comma y2. And I could come up with an infinite amount of points, more or less, on this particular object. So let's just say that we have some arbitrary point on this particular guy, and let's call it xi, yi, and it has associated weight with it, delta wi. So we're just kind of assigning an arbitrary, here's delta wi, and this is at location xi, comma, yi. So I'll put that in writing. Many individual points at locations xi, comma, yi. Sort of like the representative points on this particular plate. And let's say that each one of those points has a weight, which is delta wi. Okay. Then if I wanted to calculate like the total amount of sort of resultant force in the z direction of this particular plate, I could just sum up all of those little contributions, right? I could just add delta 1, delta 2, delta W3, delta W4, all the way up to, you know, delta Wi. So then total weight of plate is just the summation of all of those individual bits. Let's call it W total is equal to just delta W1 plus delta W2 plus dot, 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 all of these contributions, right? All of these guys added up together. This is basically like some of the forces in Z, right? It's kind of like what we're doing here. So the question is, where can I relocate that total weight so that I have an equivalent system between this infinite amount of points that are on my plate, each with their own discrete value, delta W1, delta W2, etc. Where can I relocate this here to mimic this? That's kind of the question that we're after today. And that's what I want to do. Okay. Well, let's make another assumption here, and let's assume that our plate's in equilibrium. And we've kind of done that already here with this sort of sum of the forces Z equal to 0. But with equilibrium, yes, the sum of the forces in the Z direction is 0, but also our sum of the moments also must be 0, okay? For this equilibrium to be maintained. Okay. So I'm going to do a trick here where I sum the moments about the center of this particular coordinate system. Let's call this center of the coordinate system here. Let's call this point O. O for origin. So if I wanted to, let's say, sum the moments about the origin and the x, that's going to be equal to 0. And I'm going to create sort of a new sketch here that's sort of showing what I want in my final sort of form. So more or less what I'm after, and pretend that this plate is the same plate. I know it's not the same, but pretend. Pretending's fun, okay? So where can I relocate like W total to give me like a same equivalent system as the previous one above? And so what I'm really asking is, what are the coordinates of this particular point? And typically when we're talking about the coordinates of the center of mass or the center of gravity, we'll denote them with x bar, y bar. So what I'm aiming to do is sort of replace that first drawing that I had with all those individual forces, kind of with this second drawing here, where we just have this one total weight acting at some center. And then for all intents and purposes, these two systems, analysis-wise, would be equivalent. Well, the way that we're going to do that is we're going to enforce this equilibrium, that the sum of the moments about point O in the x direction equals 0, and the sum of the moments about point O in the y direction equals 0. So let's do that. And we'll first look at our like equivalent weight system first. And that one's pretty easy. If I'm summing the moments about O in the X direction, then I have a moment arm here. If I think about like this distance, which we know is Y bar. Then the moment kind of on like the left-hand side here is just Y bar times this total weight, right? I mean, it's technically negative if you want to think about using your right-hand rule, but you get the idea based on this picture. And I'm going to equate that with my system above that has all of those tiny little weights. And I'm going to basically sum all of the moments of all those tiny little contributions of all of those individual points on that particular object. So that's going to be equal to like the contribution of the moment about X from this guy, plus the contribution about the X-axis from this guy, plus the contribution all the way up, and including like all of the contributions of all of the moments from all those little guys. So that's going to look something like Y1 delta W1, these will be negative, minus Y2 delta W2, minus all the way up to Yi delta Wi. Or if we want to sort of drop all of our negatives here, we could write this a little bit more cleanly. Y bar total weight equal to something like Y1 delta W1 plus Y2 delta W2 plus Yi delta Wi and all of the bits and all of the pieces in between. Okay. So you could do the same for summing the moments about O in the Y direction equal to 0. You'd have a similar idea. The contribution to the moment in the Y direction from that total equivalent weight is just the centroidal location X bar multiplied by the amount of weight that's acting there. And that's going to be equal to all the contributions of all of the little bits on that plate above, which will be something like X1 times delta W1 plus X2 delta W2 plus all the way up to my Xi delta Wi. And I can write both of these guys in a little bit more math functional language. And say that my X bar times the total weight is equal to the summation from I equals 1 to N, where N is the total number of points. Usually this is like from I equals 1 to infinity, but we'll get there in just a second, of what would be Xi delta Wi, and same thing for the Y. Okay. But ultimately, we're solving for this particular location, X bar, and this particular location, Y bar. This is the point on our structure where we can relocate all of the weight of the piece to have an equivalent system. And so finally, you get one of the common forms of the centroidal or center of gravity location, which is that x bar is equal to the summation from I equals 1 to n, xi delta wi over the total weight. That's one form for the x coordinate. And the other form for the y coordinate looks very similar. We're adding up all those little contributions and dividing by the total weight. So that is the location of my center of gravity, x bar, y bar. Okay, so that's a nice form. If you had some number of points where you happen to know, like, what is the weight at this particular point? What is the weight at this particular point? What is the weight at this particular point? And so as it's like currently written, like it has some use, but rare is the case where you have like all of these tiny individual little points on this object known, where they are and how much each one weighs, right? So I would say this is functional, but rare to know. All x, I, y, I, and delta wi values. Okay. Like if I'm thinking about like this table that's in front of me, and I just pick some random point and I say, what is the weight of this particular object at this point? I don't know. Like, how big is my point? Like, am I supposed to take a measurement there? How am I supposed to do that? All right. So in actuality, it's much easier to use our calculus and go from what looks like sort of like a Riemann sum. You guys remember your Riemann sums from calculus? Yeah, I'm seeing some people cry in here. I mean, shake their heads in here. Take like a summation and assume that we're looking at very, very small differential elements and take the limit more or less as these differential elements go to 0 and the number of them goes to infinity. So we can write this in the differential form using our calculus techniques. And this is a much more functional form. I'll say can rewrite in differential form. Using calculus. And the way that we're going to basically do this is assume elements of very small size with weights of dw. All right, a differential weight, dw, a very small weight. So then you get what is probably the more common form for locating center of gravity, which is the following. X bar is the integral of x multiplied by all of these little differential weights, dw, integrated over the entire volume. So more technically speaking, there should be like a volume integral here. So it's a volume, v with a dash through it. So you're integrating the contributions of all of the weights over the volume multiplied by this variable x over the total weight of the piece. Or the way it's more commonly seen, because we can write the total volume in this fashion, or the total weight in this particular fashion. Here, this is a volume integral. This is a triple integral. All right. So don't be scared. All right. We're going to talk about triple integrals and how to reduce them in just a hot second. But this is a volume integral. You're integrating basically over the whole volume. On the top here, multiplying x times your particular differential weights. So you're giving additional weight to each little individual piece that's farther and farther removed from the axis x or the axis y. That's kind of what's happening here. So this is the general form for calculating the center of gravity in the x direction, and then you have a very similar form in the y direction. It's the integral on the volume, triple integral of the y coordinate multiplied by the differential weight that exists at that particular y coordinate, integrated over the volume dw. We know that denominator is just the total weight of the piece, but it's usually written in this way so that we can be fancy. Because we fancy, son. Okay, so this is the location of the center of gravity. All right. All right, now I said that we were going to assume that this is a flat plate, and that's going to actually simplify this equation a little bit more. So let's see if we can simplify a little further. All right. So remember, we had a flat homogeneous plate. With thickness, let's call it thickness T, and specific weight, which remember specific weight is something like weight divided by volume. Sorry, not my best handwriting there. Then our little delta W's become the following. It's just the specific weight, the weight per unit volume, times the volume at that location. So let's call that delta VI. And I like to use a strike through for my volume so we don't confuse ourselves with velocity, which we're going to see in this class sometime later. If I have a consistent thickness of this particular plate, then my specific weight, I'll make sure that we know the specific weight variable here is gamma. My specific weight times my volume can be written as the thickness of the plate multiplied by the area at that particular location. All right. So let's be clear about this. This is my specific weight. This is my plate thickness. And this is my area at my point. All right. So this is kind of like the very differential form. This is like at a point. This is sort of happening. And the same can be said about the whole body, right? So we're looking at these two different ideas. Yeah, we have this happening at a point, and also in whole body, we have that the total weight is going to look something like gamma times the thickness times the area of the plate in like 2 dimensions. And so if we go back to our general equation, remember we had, let's say for the sum of the moments, about O in the y direction equal to 0, just to remind you that that was one equation that we were looking at. Remember we had like x bar times the total weight is equal to the summation from I equals 1 to n of xi delta wi. Well, if we make our substitutions now, we're going to have a bunch of canceling that happens. So we assume a constant specific weight and thickness. So it means our density of this particular piece is consistent throughout the entire plate, and the thickness of the plate is constant as well. Okay? That means that each particular point that we go to on the right-hand side of this equation has the specific weight gamma and the thickness t. And on the left-hand side, the total weight of this piece is going to contain, you know, that variable gamma and that variable little t. So let's rewrite then. So we'll get something like x bar times our total weight, which is gamma, times the thickness of the piece, times the area of the plate. Going to be equal to, we have the similar summation, I equals 1 to n of still xi times now our little pieces of weights at these particular components, which is going to be something like gamma t multiplied by the amount of area at that particular location, delta ai. Since these guys are just constant, they're going to just pop out and cancel. So we're left with something that looks like x bar a equals summation I equals 1 to n of the individual bits now multiplied by the area that exists at each one of those bits. And we can again sort of do the trick where we take in differential. So more or less delta A going to dA, and then we're going to integrate over the area. And you'll have something like x bar A is equal to the integral on the area now of x dA. Same thing in y. All right. There's a nice picture in your notes that sort of like walks through this pictographically. And I am going to bring that picture from the notes in here. If you'd like to copy it down into your own notes, that's fine. Otherwise, if you just want to make a reference back to the slides themselves, you can go ahead and do that. And so we'll say pictographically or pictorially the following. If you're looking at this plate now head on, it's going to make a little bit more sense. So I stole this from a book. Sorry about the image quality. I think it's good enough to pass. But here's the idea. You're looking on this plate head on, and we can sort of like separate it into these like aerial elements, right? So you see all those like little squares there. And if we're going to say that it has constant gamma and t, that means the thickness of this plate into the page is constant, and the specific weight at any particular point or the density at any particular square is the same. Then we can look at any particular location, and that's going to have an area of delta A, and that's going to have a location of xy, or what we call xi and yi. And so we're basically integrating over this entire thing and looking at where we can relocate to give us like this like y bar and x bar. And so integral x dA over A is going to get us there, something like that. Right. So this, I think, a nice picture of it. Okay, we'll break here for 10 minutes. We'll come back at 5:57 and continue the lecture. If you want to keep going on this picture, you can go ahead and do that. Okay, 458. Welcome back to your favorite class. Yes. Okay, so let's get back into it. We're just kind of talking about this formula for calculating the centroid of just generally like a two-dimensional homogeneous plate. And so here we are with these two general formula. And more commonly, you'll see these formulas in the following way. And I know I've written a lot of forms here, but this is seriously the most common form. Here, the integral on the area x dA over the integral on the area dA. So we've kind of taken the area from the left-hand side, moved it to the right-hand side, and now we're writing the area as an integral instead of a total area. Because if we have some crazy shape or whatever, might actually be easier to sort of calculate that integral. Similar looking equation for y, integral in the area, y dA over the integral on the area dA. These are the most common forms of the centroid equation. All right. And we'll note here that the integral on the area of the differential area by first fundamental theorem of calculus is the total area. So if you happen to know the total area of the object, just don't do the integration, just put it in there. Okay. Pretty easy and obvious for that one. Okay. Now let's talk about how to actually work with these equations, because you look at this and it's a little bit daunting. That area integral is a double integral. So I think some of you are probably going through Calc 4 right now. Yes, you said Calc 4 to talk about double integrals, and maybe you're just like first sort of learning how to do double integration. So guess what? You're going to get a double dose of it. So we're going to learn it a little bit in this class. If you're not comfortable with double integrals, I will show you how to do this with single integrals, but I encourage you to sort of learn how to do this with double integrals, because I think it's the fastest and easiest way once you're sort of comfortable using that sort of technique. And as engineers, don't be afraid of math. Damn it. Like, you're going to have to use high level math and you just have to do it. All right. So don't be afraid of double integrals. If you want to do it single integral way, that's fine. I'll just encourage you to maybe sort of like learn how to do it double integral way. All right. So now executing or using this equation. Okay. So let's say we have some random shape and we're interested in calculating like the centroid of that particular shape. So let's say here we have a two-dimensional plane, xy, and we're going to make some arbitrary plate in 2 dimensions, and we're interested in utilizing the equations that we just derived to calculate the centroidal location of this particular object. So let's say we have an object here. I'll do it in blue because, you know, why not? Okay. Here we have this particular object. I don't know, some plate. All right. And there is some differential area that exists in this plate. I'm kind of blowing it up here. But here, this is a differential area dA. That's what we're going to assume. And we're going to say that it's located at the location, xy. So here, this is distance x. And this is your distance y. All right. So now we want to move forward with trying to utilize our equations. So in Cartesian coordinates, which is what we have here, our differential area dA is dx times dy, or dy times dx. All right, it's not kind of a stretch, where we assume that this guy has some like differential height, which is dy, and he has some differential width, which is dx. Okay, so dA is dx dy, or dy dx. Commutative property of multiplication. Yes. All right, my favorite property. No, I think Michael Jordan's Mansion is my favorite property, but okay. Someday I will own it. Okay. All right, so in Cartesian coordinates, this differential area can be separated into like this dx times dy, okay? If that's the case, then we can sort of rewrite our crazy centroid equation as a double integral. Something like x bar is the double integral of x dx dy over the double integral dx dy. This is the same thing as like the single integral x dA over the single integral dA. It's the same idea. Equivalently, we could write this as x dy dx over double integral of dy dx. Right. And we could have a similar looking thing for y. I know it seems like I'm beating this to death, but let's just get it down. Nope, sorry. It's just okay. All of these things are kind of like equivalent to each other. It's just because of this commutative property of multiplication, we can sort of rearrange how those differentials are presented. Okay. Now let's talk about how we like execute this now. So for all these guys here, when we're going to execute this, we're going to consider the following. The difficult part of these double integrals really is the limits. All right. So when we're integrating these guys, we're integrating them sort of like from inside out. Just like the Disney movie. All right. That's what it's called, right? Inside Out, with like the feelings have feelings. That's Disney's model, okay? What if these toys have feelings? Toy Story. What if our feelings had feelings? Inside Out. There you go. What are some of the other movies where things that are usually, what if cars have feelings? Okay, Cars. There you go. All right, so we're integrating from inside out. What do I mean by that? Well, this is sort of how double integrals are generally attacked. So if we wanted to like attack this double integral here, what I'd want to do is I'd want to execute this internal integral first, get some solution for that contains the variable y, and then execute my outer integral after that, okay? So that's what I mean by integrating from inside out. This would be first, this would be second, all right? And so you can execute that over and over and over for all of these particular integrals. And so if you know how to do a single integral, the idea is just do the single integral twice, you know? The one on the inside, you just execute as a single integral, do your integration. You're going to get some function. Then integrate again with respect to the other variable. Here now would be with respect to y on the outside. You could do a similar strategy, but just sort of rearrange the integration if it's more convenient for you by using that commutative property I talked before. So in this situation, maybe it's more convenient to integrate with respect to y before integrating with respect to x. Either way, you get the same answer. Just make sure you're working from the inside out, right? So that's what I mean by integrating from inside out. The limits here are governed by relationship between x and y. Usually, boundaries of objects can be written as either x is some function of y or y is some function of x. Okay. What do I mean by that? Well, if I go back up to this particular figure here, I might know that this particular line here is y is equal to some function of x. Okay, this is something you learned kind of back in your like algebra class. Right? I also know that this particular boundary can be written as something like x equals some number. All right. That boundary can also be written as x equals 5. All right. So it's kind of like writing it in terms of a value. Maybe I'm giving myself a lower limit down here, which is something like y equals 0. So the point is all of the size of this particular object can be written in terms of like some function or some constant, or just kind of depends on what you're working with, right? And then once you've sort of established what the equations are that are sort of governing the boundaries, you can work through your double integral appropriately. And so let's spend the rest of the time today going through one particular example, and we are going to beat this example to death. You're going to be sick of this example by the time we're done, all right? So we're going to do a single integral method for calculating this guy. We're going to do double integral methods with dy dx, with dx dy. You're going to see it all here, baby. So we're going to go through an example, and we're going to utilize the techniques of these particular equations and utilize double integral, single integral techniques to actually calculate the location of a centroid of a sort of rather strange looking object. Okay, so here's the prompt, very simple. Find the centroid of the homogeneous flat plate shown. That's your prompt, and here's your figure. All right. No numbers, just symbols. Everybody groan. Oh, God, I hate it when they don't give us numbers. Oh, okay. I'm glad that's out of your system. So more or less, we're looking for x bar, y bar. And it's going to help for me to establish a coordinate system here. It's sort of kind of already implied by the function that's given. But I'll make it crystal clear. Here we have x, and here we have y. So I want to find the location of that centroid of that object, x bar, y bar. Okay, I'm going to help myself out a little bit here by assigning equations that represent the boundary of this object. So if I wanted to write an equation for that particular boundary, that straight vertical line, what is the equation at that point? Someone.
X equals and then a number.
X equals A.
An equation for this vertical boundary here. Not y equals A, close. X equals A, good. Okay, so that's that kind of boundary down here. And if I want to establish an equation for like the boundary that's kind of the bottom of this particular piece, now we're ready for you. Perfect, y equals A. Well, not y equals A, y equals 0. We're at the bottom. I knew what you meant. Okay, so these are kind of like the equations that define the boundaries of my plate. Okay, plate. All right. There's also one other piece of information that's going to be helpful for us here, and that is to define this point up here in terms of A and H. All right, so obviously this point here is A comma H, right? So this will be important for us in helping us like define the boundaries of this particular piece. So that point there is A comma H. Last thing that's going to be helpful is finding K. In terms of A and H. So we're going to assume that A and H are kind of known values and K is some other constant. Rather only have 2 constants floating around than 3 constants floating around. So how can we solve for K in terms of A and H?
K equals H over A squared.
Excellent, very good. So we have this function here, y equals kx squared. And so we can substitute the point x equals A, y is equal to H into that to solve for K. So we know from that function that K is y on x squared. So that means here that K, when we plug in that particular point that we know is on the line, is going to be H on A squared. I'll mostly keep it as K as we move through the problem, but we can substitute that K as H on A squared kind of at the back ends of these particular problems. All right, so our geometry is kind of like settled, and we're more or less ready to sort of attack. Okay. So regardless of kind of the method that we choose, this pesky like integral a dA keeps popping up. So regardless of the direction that we go, we're going to need to sort of execute that integral. All right, so let's work on this particular integral here so that we can calculate the area of our piece. This is going to be like stepping stone number 1. So first, let's calculate. This integral a dA. We're going to do it in a couple methods, just so you can sort of see all of these methods in all of their glory. Method number 1 will be with a single integration method, which is probably methods you're most commonly used to for your calculus classes. And then methods 2 and 3 will use double integration, one with dx dy and one with dy dx, just so you see the differences and understand how double integration is performed. All right, so let's go method 1. We'll say single integration. All right. If you're going back to your calculus class and you wanted to try to calculate the area of this particular object here, how would you do that? How do we calculate the area of underneath a function?
The integral from the start to the end of x.
Yeah, we just integrate the function. Okay, so single integral method here would be that the area is just the integral of y is a function of x dx. What are my bounds on this particular guy? If I go back up to my figure. Zero to a, good. From 0 to a, all right. So this is your traditional like single integration method. Nothing too complicated about this. We're here now, so this is kx squared dx, so I'm just plugging in. All right. We know k is just a constant value, so we can execute this as x cubed on 3 with bounds of kx cubed on 3 with boundary 0 to a. Let's plug in what we know for our variable k. So this is obviously k cubed on 3. And now we plug in for k. We'll have h on a squared. It's our constant value k times a cubed all over 3. And so the area of our piece here will just be ha on 3. Okay. That's your traditional method for calc 1. It's your calc 1 method. Let's up our game. Level 2, baby. Level 2. Double integration. And here we'll specifically do it with dA is dx dy. All right, so now we're going to work through a double integration. If you don't like this method, that's okay. Just try to hang on with me and maybe pick something up on the way if you can. So remember our area in this particular problem is the integral on a of dA. But now we're going to make the substitution here that dA is dx dy. So we're going to introduce here our double integral. Okay, so here's our double integral. And dA is, we're going to do dx dy. And as I mentioned before, we're going to be integrating from the inside out. Right? So the first integral we're going to do is here. And the second we're going to do is here. So this internal integral here, I need to determine what my bounds are on this internal integral. And I need to write my bounds in terms of the function y, okay? So no longer am I integrating sort of across discrete values, but I'm integrating more or less across sort of the width of the function at this particular location. So if I consider like what is going on this interior portion of the integral, I'm integrating basically in sort of this direction across dx. And so my limits as I'm integrating on dx, as I'm moving from this particular line, which has some certain boundary, to this particular line, which has some certain boundary. Okay? So my limits for this particular integration, this portion of the integration, is I'm going from on the left-hand side, this boundary, to on the right-hand side, this boundary. Okay? So the appropriate limits of integration for this particular part the left-hand boundary written in terms of y is going to be the square root of y on k. All right. So the left-hand boundary, x, written in terms of y, going back up here, notice that this can also be written as x is square root of y on k. Okay. So I'm going from that left-hand boundary of x to the right-hand boundary of x, which is x equal to a. All right. Now I have to consider my limits on y. And the only time I really have to concern myself with these weird limits of integration hitting this line is sort of the internal portion of the integral. When I'm integrating on y, now I've sort of like dealt with that function, and I'm just interested in sort of like the absolute limits of this particular function. So on y, I'm going from the bottom limit of y equals 0 to an upper limit here of y equals h. All right, so that's my upper limits of integration here. So on the outer portions of the integral, we're going to have something like y equals 0 to y equals h. So this is my full double integral here. All right. Raise your hand if you have done something like this before. We have one person. Whew. That makes me nervous. Okay, now someone else. Well, you'll see this shortly in your Calc 4 class. God, I hope. Maybe stick with the single integration method until you get a little bit more description. But you're getting a taste, you're getting a flavor. It's funny, last time I taught this class, I think people had covered it already at this point. So
there were people in here that raised their hands too.
So we're going to execute the first interior portion of this integral first. So let's do that just like you would traditionally do some integration. All right. The integral of dx is just x. Okay. So let's execute this interior portion of the integral. And we'll keep and retain the outer portion of the integral as we go. And so after I sort of integrate my integral dx, I'm just going to be left with the variable x integrated over the boundary square root y on k to a. Okay, so this represents that internal integral that I have just executed. Okay, so let's continue with that. Still retaining my outer bounds. Y equals 0 to y equals h. And now I'm just plugging in for my traditional integration on the inside there, which would be something like a minus root y on k. And don't forget my differential that's still hanging out here, dy. All right. Now I'm going to execute my sort of outer integral. And we see that everything that's inside of here is written in terms of y. See, we still have an integration variable here, which is the integration variable y. So we sort of have to deal with this through our integration. I'm going to cut to the chase here and just kind of write this integral and what it looks like afterwards. Obviously, the first bit of this is just going to be ay. Once we integrate a constant a with respect to y, we get ay. And after integrating this sort of weird radical, it's just basically like 1 on root k times root y. Wouldn't be that difficult to sort of execute this. 2y to the 3/2 power over 3 root k. And evaluating this from 0 to h. All right. Executing. Minus 2h to the 3/2 on 3 square roots of k. But here we can plug in for k. It's going to be h on a squared. Just plugging in for k. We solved for this previously. Do some simplification here. This is ah minus just 2/3 ah after all that. Got like 3/2 in the numerator here. You got 1/2 in the denominator. So it's just going to give you 1h left over. And you have 1a in the denominator here. That's going to come to the numerator. So you have ah minus 2/3 ah, or finally, the area of this object, 1/3 ah, which is the same area we calculated using the single integral method. Hot diggity.
What would be the advantage of using the double integral method?
All right, let's go one more time through this technique, but let's sort of flip the way that we do this. I think I have a question. What would be the, I can't hear you. Can you speak? Say something to make sure I can hear you.
Hello?
Hello?
Oh, man, can't. Okay, go for it again. Why this thing's on mute? Sorry, guys. Yeah, if you have a question, go ahead and type the question into the chat and I'll try to answer. I think it's working now.
Hello?
Yeah, I got it now. All right, so I can hear you guys now. Sorry about that. What would be the advantage of using double integral method? We'll get to that. It is advantageous later. I know it seems like kind of a pain right now, but. All right, so let's try this one. Just give you another exercise here. Flex those math muscles. Roar. Roar. All right. So here we go. Again, this is going to be our integral dA on A, starting from the same general location. We've got a double integral again, but here now we're doing dy dx instead of dx dy. So our internal integral now is going to start with sort of the y direction instead of the x direction. So here now this internal integral is what we're considering first and what we're thinking about first. And now I want to consider the limits on my y direction for my object. And that's what's going to go kind of like here and here. Okay. So I first have to consider sort of like the limits on the y integration now for this object. So let's go all the way back up here. And now I'm considering these limits as I'm sort of like moving across x. What am I running into on my lower boundary and what am I running into on my upper boundary? Well, my lower boundary is pretty obvious. I'm contained in the y direction by y equals 0. In my upper boundary, I'm contained in the y direction by y equals kx squared. So my bounds of integration on this particular guy, on the interior integral, is from y equals 0 to y equals kx squared, right? Okay, then on my outer integral, I have to worry about my limits of integration for x. And here, since I've already accounted for my function, I just need to know the absolute limits along x. The absolute limits along x, I'm going from x equals 0, which is here, to x equals a, which is here. So these are sort of my limits in the x direction. All right. So we'll do the interior integral first. While still retaining my exterior. So the integral of dy is just y. Here on the bounds of 0 to kx squared. Don't forget my dx. Plugging in. The integral here is obviously, after plugging in, is just going to be kx squared minus 0, or kx squared. Result here, be k on 3, x to the third, evaluated between 0 and a. So ka cubed on 3. Plug in for k. We know that this is root h on a squared. Sorry, I forget exactly how it was. Oh, sorry, k is, yeah, h on a squared. Sorry about that. A cubed on 3. And here we're going to have HA on 3. So again, the same answer that we had previously. Okay. So in brief, we just looked at 3 methods that the area here is HA on 3. So when we look at our centroid equations, that's going to be our denominator that we're working with. Okay, so that'll be it for today. We'll pick this example up on Thursday and keep beating it into the ground with our math fists. That's it for today. Thanks.
Thank you.